Hello, everyone. Good morning. Hope you can hear me OK. Get my optimal mic position set up here. Wonderful. So it's great to be here. And today I'm going to be speaking about this topic of closing the sim to reality gap, especially using Unreal Engine 5. I'm Sai Vemprala. I'm from General Robotics. So we were recently, up until recently, we were called Scaled Foundations. So if you saw that name on anything related to the session, just know that we've rebranded and now we're called General Robotics. So a little bit about myself. I spent about 4 years at Microsoft Research prior to starting this company. I worked on the intersection of foundation models and machine learning and robotics, where simulation is a huge component of it. Prior to that, I'd received my PhD from Texas A&M, where I was mostly working on drones, doing computer vision and path planning, and so on. So overall, I spent about a decade at this very interesting intersection of machine learning and robotics. So I'd love to share what we found collectively, over the years and where we're trying to go, and how the technology from Unreal Engine is really supporting this journey. So for this talk, I'm mostly going to focus on a little bit of like an outline of what the problem really is for robotics, especially in this day and age of AI contributing to the efforts in robotics, and how in our prior works, like how we've tried to kind of tackle this problem of how do you build a good simulation for robotics, and what do you need from a sim to really solve robotics at scale. And specifically, it boils down to, just like in gaming, it really boils down to the environments, right? So you've got these agents kind of living in, interacting with these rich worlds is what you really want from a sim. So how do you construct that? How do you get those rich behaviors and environmental kind of like considerations taken care of and so on? And then I'll move on to kind of describing where we are today, generally like at our company as well as in the field, and finally kind of wrap up with some opportunities and challenges and things like that. So hopefully make for a healthy discussion afterwards. I'll skip this one. I think I've already done it. And thanks, Nicola, for also introducing me real quick. OK, so kind of starting off with what's the problem? This is always a good starting point. A lot of us know that AI is very data hungry, right? So, I mean, we've seen these massive data sets kind of contributing to large language models and computer vision models and so on. And generally, when you talk about robotics, the availability of data is a problem, right? We don't have that level of web scale data or image scale data that people typically use for these models. But at the same time, I mean, these robots are, at the end of the day, running in real world, which is a fairly challenging endeavor. You have so much diversity, so much variation in what these robots are expected to do. And most importantly, I also believe the challenge is partly the fact that it's not static data sets. It's not about like, oh, a bunch of text or a bunch of images. It's really these streams of data that are about behaviors. Like, how do you pick up an object like this? Or how do you have a navigation robot kind of go through this room and maybe interact with people or something like that? So behaviors, it's kind of like an exponentially harder thing to simulate and get right, and especially create the level of variation that you want. And that, again, leads to environmental variation. So you've got robotic arms, you've got quadrupeds, you've got humanoids and drones, and they all live in very distinct worlds, or expect to live in very distinct worlds. And at the end of it all, I mean, this is a little bit beyond maybe what we're discussing today, but also testing these models, like if you've built any AI models, like testing them in real life involves obviously way too much effort and has its own challenges. So can you train using simulation? Can you test using simulation? Is there a concept of like a robotic CI/CD almost, where you're using simulation as a primary component to that? So all of these are open questions today, and solving all of them, I think, is pretty much required to really get to robotics at scale. And really just building upon that, everybody has a lot of aspirations for robots, but robotic intelligence is so inaccessible even in the current day because, again, the scarcity of data, scarcity of experts, and really this notion that field robotics is a very, very complex endeavor. You need people who know hardware, people who can do ops and who can kind of deploy machine learning models and maybe test out like 5 or 6 different versions of them. And it's a huge effort, like all in all, going end to end. And at our company, we were doing some research on this particular area, and we've had a few articles that we put out recently that kind of alluded to the fact that when you compare the level of activity in AI and you take that and you kind of contrast that with robotics, there are not as many people working on robotics because of all the perceived challenges in this field, and the data sources that you have to really prototype or test or train anything are far, far smaller, right? So you've got hundreds of thousands of data sets on things like Hugging Face for general AI. But if you think about large-scale robot AI, it's not there. And even collecting the data is immensely hard. So to that effect, I mean, robots that are out there today, unfortunately and somewhat ironically, they're still being manually operated, at scale, right? So that's what we want to solve. Like, how do you get to some level of autonomy, and how do you get to a place where you don't require a ton of human attention to, have them do what they're supposed to do? And this is this is an interesting little video. This kind of shows like, a couple of seconds of a mishap in field robotics means maybe thousands of dollars or maybe another week or something like that. So it's very expensive in terms of time and resources. And you've got, I listed out some points here, like, there's travel, there's logistics, like how do you set up your hardware? How do you get the location right? How do you set up the use case of your interest in this location? And I'm from Seattle. Our company's located in Seattle, and those who are from the Pacific Northwest, that there is a very small window where you can actually go out and fly a drone or something like that. If you're doing indoors, that's good, but not for stuff like this. So you have very limited windows for these kinds of things. So that actually was a huge factor in us developing our early efforts in simulation and really starting to look at Unreal Engine and so on. So, and also, historically, robotic simulators have really kind of focused on physics and like an abstraction of behaviors, and not so much visuals, right? Because again, maybe it just took a little while to kind of catch up with the advances in computer graphics and simulation. But I think a lot of these simulators are still being used today in academic contexts and also some industry contexts where people are really kind of like trying to get the robot dynamics or like the robot kind of like motion planning or trajectories kind of right. But there is still a bit of a jump from going from that to realistic visuals and realistic kind of data. But for true robot AI, that's what you want. You want realistic visuals from which they can learn how the world works and so on and so forth. So we believe the solution really is, okay, how do you leverage the power of graphics, of course, to enable simulation and to bring all the goodness of the gaming world into the robotic context, so robots can now operate in these kind of like living, breathing environments, but also partly, how do you leverage the power of the cloud? Because at the end of the day, you need to train these models at scale, right? So you need these robots to experience 10x, 100x at 100x the scale of real time to really kind of like learn these behaviors faster. So which means likely parallelization, and that involves obviously multiple resources, probably spinning up on the cloud, kind of sitting there, training these models, testing these models at scale, and so on. So what we wish to do is really, the first question is, how do you enable, of course, multiple kinds of robots in an ecosystem like Unreal Engine 5 so that you can benefit from all of the features in there? This means, again, robotic arms and drones and quadrupeds and so on and so forth. Each has its own kind of like nuances and complexities. And how do we provide a variety of environments for them to train on? And I'll kind of go through how much variation there typically is when we think about environments for robots. And finally, how do you train, test, and deploy? But it's not that simple. It's easy to list down what we want, but how do we actually make it happen, right? So, for example, what does a robot need to do? It really depends on the skills that you're trying to build. Again, this is dependent on the form factors, and even within a form factor, you have infrastructure inspection is a task versus, for example, it could be a ground robot kind of like going around inspecting something, but it's a completely different ballgame if there is a ground robot inside a building, kind of like going from room to room. So it's a lot more constrained of a problem to navigate through like complex layouts or something like that. And similarly, so how do you, if you want to have, like, for example, a robot operate in a human-packed kind of a space like this one, then you have to enable those actors, and maybe there's some human-robot interaction component over there or a social robotics component over there. Like, how do you get all of those kind of encoded in your scenes and your simulation? And what is your sensing layer? Robots typically operate with cameras, LiDARs, and a whole bunch of other things. So there is effort involved in kind of setting all of those up in the simulation as well. So what do we want our system to do actually results in kind of like this huge array of branching logic on what you would expect from the simulation to have to really kind of accrue to the final goals. And so taking all of this into consideration, I'd like to talk a little bit about some of our early efforts in the space. And this was actually from the time when I was at Microsoft, and there was a team of us kind of working on integrating robotic simulation with Unreal Engine. So this was with Unreal Engine 4. So this was called Microsoft AirSim. And this was released in 2017 as an open source project. It still continues to be a fairly popular kind of platform for specifically drone simulation, wheeled robot simulation running on Unreal Engine. And the intent for us, like I said, primarily was to get out of the Seattle weather complexity, but also ask this question of how do you do large-scale data collection? How do you get these drones and ground robots to fly around in worlds that look like this? And Unreal Engine 4 was bringing in so much technology from the gaming world kind of like into a development package. So we were able to pull off some complex kind of city scenes and realistic traffic and weather and time of day. I mean, you can kind of think of all of these different variations you typically see in games, right? And this allowed us to put these robots and collect these data traces from very kind of randomized versions of scenes and realistic environments. And I think we have some NPCs over here. This was mostly for some wildlife kind of related projects. So this is just a summary visually of some of the things that we were trying to enable here. So it involved robots in different worlds and sensors, data collection routines, so on and so forth, just to kind of get all that in one place. And yeah, and then you can also have the different kinds of cars and drones and different camera views, looking forwards, looking downwards. Again, it was very trivial to kind of enable all of this kind of building upon the Unreal stack. And some of you might recognize this particular demo. This was the kite demo from, I think, 2015, 2016. And the first thing we did when we did AirSim was, OK, let's put this in the kite demo scene. So because it was one of the, I think it was probably like one of the first efforts of like a geo-referenced, a very large-scale scene, which was amazingly good, right, for that time and day. And we realized that the fact that we can even render stuff like this at real time was huge for robots. So you could do even things like reinforcement learning. You can have, again, data sets of very complex things like, maybe these, kind of animals running. I'm trying to figure out what they are, deer, I guess. Running around in the scene. And imagine the amount of effort you would require to actually get a real data set of this. And the animals are critical to the next slide, so which is why I'm putting a little bit of focus on that. But overall, like high-fidelity scenery, NPCs, large-scale weather variations, and so on and so forth, again, all kind of accrues to building robust robotics. And why were the animals critical? Because there was actually a project specifically using AirSim for poacher detection from infrared video. And on surface level, it's a hard problem, right? So you have to look at infrared imagery. You have to understand, OK, how do I detect these little hot spots of humans and not the animals as kind of your target of interest? It's a low probability scenario. You obviously don't have a lot of real life data corresponding to that to train a machine learning model. So simulation is their only bet. So this was led by a group of folks kind of using AirSim to first create a large-scale world of like animals running around in African savanna kind of an environment. And then through AirSim, we also were able to simulate infrared imagery to some extent. So what you're seeing on the top left is actually a real, well, not real, but a simulation RGB video. And then over here, you have like a simulated infrared video, which you can tell that it doesn't look super, super realistic, right? I mean, it kind of gives you these hot spots of some animals kind of tracking over here. We have the rest of the trees at a different temperature. And as you know, in IR, you have different ranges of all of these. But what this project did was actually use generative models to kind of make these simulated infrared imagery more realistic so that they will actually look like what the real IR camera would look like. And eventually they figured out that by training generative models on simulation data like this, you are almost getting real data for free. Because at the end of the day, if you train it right, you can now generate realistic looking versions of infrared from very, very different scenes. And they were actually able to deploy this in real life and achieve success in human detection. So this was one of the very first proof points for us that simulation data actually works, especially if you augment it with some of these fancier techniques like GANs or generative AI. But even in general, for things that are easier to simulate, like RGB cameras or depth cameras or something, you can actually take it out of the box and be able to make progress with it. And finally, geospatial was a huge interest, I mean, in the community even now, and then even for us. So back then, when we were doing AirSim on Unreal Engine 4, some of our attempts with large-scale geospatial were using a lot of kind of like this hodgepodge of tools out there. So this is actually a prestigious orb viewer, which would wrangle a lot of different data sources and then put them in an Unreal-friendly format. So you have some ground terrain data, you have some building data, maybe coming from like OpenStreetMaps and those kinds of things. But it was still a little complex. Like you actually had to go through a lot of work on kind of like a per region basis to kind of get those tiles ready, make sure you've got the right terrain, maybe from USGS or something like that. And overall, it was somewhat time intensive. So although the intent was there to simulate like a lot of geospatial, georeferenced scenes, it did involve a lot of effort. So that it kind of like brought up this question, okay, how do you solve it going forward? Especially with robots hoping to become more integrative parts of the daily reality. Okay, so that was kind of a few things that we did over the years. So this, again, all of us part of like an open source project that we did at Microsoft. And then I'm going to move on to kind of like how we are doing it now, kind of learning all these lessons from the days of AirSim. And this is in the context of what we are building at General Robotics, which is called the General Robot Intelligence Development Platform, where Unreal Engine 5 is an integrative piece. And yeah, I'll basically talk about how we are leveraging all the novel features from Unreal to kind of solve these pain points and hopefully kind of pave the way forward. So just as a summary, what this platform that I'm talking about really does is it's a means to access, develop and deploy robot intelligence. So as we can imagine, simulation, again, is a primary component in this notion of developing robot intelligence because that's where you prototype, that's where you simulate your use case, and that's where you test. And through the platform, we have these simulations powered by Unreal Engine, and then we have access to a bunch of AI models, like foundation models that are out there. For example, computer vision models or robotic-specific models and so on. And through all of that, you now have access to an interesting stack where you can take a robot of your choice, you can put it in a simulation, you're leveraging a bunch of AI skills for it, like obstacle avoidance or autonomous flight, and really generate some data, test your models, and finally kind of deploy. So this is kind of like an overarching view of what the platform really is, and kind of using this context to talk about how we are trying to achieve this. And of course, it's not a presentation without a bunch of block diagrams and wiring kind of connections. So I just wanted to pop this up there if you're really interested in how the platform kind of works. So our simulation is now called AirGen, which is kind of like building upon our past work on AirSim. It is powered by Unreal Engine 5. We're hoping to upgrade to 5.6 soon, but getting there. Really, if you think of this as like a multi-layered process, we've got the simulation kind of forming the base layer where you have multiple scenes and multiple robots and sensors, all that you can access. And then you're augmenting all of that with these data generation capabilities or ground truth generation capabilities. Like how do these robots really even know how to do the basic stuff, like approaching a certain object or navigating through a space? You need that in the simulation layer as this ground truth that a baseline that they can learn from. And upon that, we have kind of like these more, I would say, API layer kind of things, like how do you leverage AI models upon the simulation? How do you, in this day and age, what is it without a copilot? So we also have an LLM copilot that kind of knows the API of the simulation and can wrangle it to some extent to get what you want or help you kind of leverage the AI models. And upon all of that, this is basically like the front end would involve, obviously, if you're running simulations, you'd have to find a way to stream them. If you are using robots in a sim, you'd have to find a way to visualize their telemetry, like their cameras and so on and so forth. So we have this front end that kind of like combines sim streaming with some interfaces for like the code and the LLMs. Things for example, operators would be very different from people who are developing. So all of these things are also kind of form the top layer of the platform. But what we're going to be speaking about mostly today is kind of like the base layer, which is the simulation layer, and which we call AirGen. Okay, so diving a little deeper into the simulation, the very first thing that comes to mind, came to mind when I was making this was basically environments, right? So we had this, when we were doing AirSim, the first thing that we realized that, yes, you have a lot of access to very rich environments now, But you also need certain hooks in the environments to really match realistic use cases. It doesn't do to just pick up some random scenery and have a drone or something in there. And yeah, I mean, it really depends on what you want your robotic systems to do, right? So you've got all of these distinct industry use cases today. For example, agriculture. Like autonomous agriculture means you need farms, you need these specific agricultural robots that have a certain kind of make and model or like dynamics and stuff like that. Sometimes these things actually come equipped with arms so that they can go pick fruits or something like that, which is obviously a lot more complicated than just having a wheeled robot. But when you're thinking about agriculture, people have these needs of being able to spawn like procedural sections of certain crops, and you would want to maybe vary things like spacing or how many plants do you want and what the height of those things are. Maybe they evolve over time so you can actually simulate the behavior of the robot with different stages of your plant's kind of growth. So it's a huge kind of ball game in itself, right? So there are things like that that would really have to be factored in when you're developing environments. You can talk about stuff like warehouse automation. Now you have forklifts, which are maybe multiple of them in warehouses, kind of like going and coordinating with each other. They need to go pick up boxes and leave them in a different place, and you'd need all of these individual objects to be kind of like movable and kind of have their own physics and everything like that. They're not just static, rows of shelves anymore. So that's something again we'll have to go build. Things like infrastructure inspection, it's pretty huge in the drone space today, both drone and the other class of robots, which often involves these, not so niche, but I guess maybe more niche from like a gaming point of view, stuff like turbines or solar panels and different kinds of buildings and so on and so forth, cell towers and stuff like that, which are not historically things that are hugely represented. So often there is effort involved in building up these objects or maybe scanning real life objects and bring them back to sim. So again, everything is a rabbit hole in itself, or can be a rabbit hole in itself, depending on the approach that we take. And really the challenge is how do you scale that kind of process, right? How do you break out of this notion that we have to develop something very custom for each of them? And similarly, there is delivery robots, which means suburban scenes and maybe humans on the sidewalk and some traffic and stuff like that. Space robotics, the final frontier, or maybe not so much, maybe there's more. But then again, you're looking at low gravity scenarios and interesting wheel dynamics and how it kind of like interacts with the terrain and that kind of stuff. And of course, there is these worlds that the robots will inhabit, but what do you want to do in those worlds also determines how you build those worlds. Do you want to train like an object detection model, which means you'll have to be able to put certain objects of interest in the scene and then put them in different locations and different lighting conditions and different poses and so on and so forth. So you need hooks. It's not just a static world anymore. You need to be able to randomize it in hundreds of thousands of different possibilities, pretty much. So that's there. And then I think this kind of goes back into the infrastructure inspection scenario. But the reason I wanted to highlight this particular thing is actually, I'll touch upon this towards the end. This is actually a project that we're undertaking with a company called Raptor Maps, which does a lot of solar panel inspection using drones and wheeled robots. And this is a cross-form factor collaboration scenario. So you've got two different kinds of robots that need to work with each other and be aware of each other and so on. And tying it all together, the holy grail is, I think, a lot of people have kind of like discussed this and attempted this over the years, and we're getting very, very close to this notion of this holy grail of environments, which is, this large scale, almost like Earth scale kind of scenery where you can actually go all the way up and down in your kind of like heights to different LODs, and then you have high altitude data from like low fidelity, but then low altitude with high fidelity with actual buildings and probably even streets that kind of match the real, street maps, and you've got traffic inhabiting all of that. You've got, pedestrians walking around in parks and sidewalks. Of course, that's what we would love. Of course, we're still trying to get there. But we do have a lot more options today than what we had like 5 or 6 years ago when the Prestigious Orbviewer thing that was built. So we've got, for example, the cesium platform. A lot of you might be familiar with that for bringing in geospatial data. It works with many distinct data sources, and we make good use of that. There's obviously other players in there like Black Shark that are trying to do like a procedural generation of buildings and building footprints and then placing them in specific locations and so on. So a lot of work is happening indeed, and it is definitely accruing again to this grand goal of creating these worlds for robots. There are still some challenges. For example, a lot of these data sources excel at kind of like high altitude data, but if you get close to the source, like for example, close to the ground, example with like Google Earth, right? So, I mean, it looks great from this kind of a viewpoint, but if you go all the way down, you realize that the buildings are a little janky and things like that. So there is a lot of interest today in the drone world on kind of like air taxis or like personal kind of like aerial transport or general aerial transport, which means those vehicles are kind of like taking off from or landing on specific buildings. So they're really much closer to the ground, as opposed to just, for example, say like an autonomous aircraft. You can kind of like abstract away the takeoff and the landing, and you just have like mission planning for the entire thing at a high altitude. But for stuff like eVTOLs or these personal kind of like air transport vehicles, it's a little bit different. So ground detail is something that still needs to be figured out to some extent. So then I want to spend some time talking about the current state of the tech, and then how, in the context of how we are leveraging it, I'd like to kind of, showcase a few things on how specifically the Unreal technology is benefiting the sim that we're building, and also the industry in general, and hopefully kind of like lead on to some interesting discussion points there. So the first thing that we were able to kind of take advantage of with Unreal 5 was the ability to simulate large-scale environments. This is obviously coming from a combination of things. You've got things like Nanite kind of helping with these massive levels of geometry. A lot of you might have seen the Witcher 4 demo this morning where Nanite's going to go into the next level. Would love to make use of that sometime soon. But really, I think that combined with, of course, Nanite, Lumen, and also all of the mass AI kind of plugins for realistic NPCs means we can build, for example, very interesting worlds like this, where we've got this vertical takeoff and landing vehicle in what looks like a very large-scale city scene. So you actually have, like, although there might be some repetition kind of like at a certain point out there in the distance, it gives you this notion that there is a dense scene around you, as opposed to just being like one city block. And it might be a little hard to see, but there is actually some traffic down there kind of like going through the roads. And in this video, we were kind of like varying the weather conditions and so on. So this is all running on Unreal Engine 5 through our AirGen sim. And this is probably not a very safe thing to do for an eVTOL, but we just wanted to showcase the road level details. So you see all the like reflections and the glare and some of the traffic and so on. All of those things kind of matter. There's always like, you can get to 90%, but getting to 100% is actually a huge jump. So you've got, I think we've seen through our years of experience in this world, drones failing for the weirdest of problems, for the weirdest of reasons. It's just like, oh, there is glare from a car in my front-facing camera, so I'm screwed, so I cannot fly anymore. And so you'll have to play around with, okay, do I look at a bottom-facing camera? Do I look at a front-facing camera? And all of those decisions, you would only think about them if you can simulate the possibilities. And you don't want to wait until you get to a real-life test to simulate them, because safety is obviously paramount when it comes to robotics. So being able to kind of get to that level of fidelity and size and scale and NPC kind of behavior is huge for robotics. And more interestingly, I want to spend some time on this. There is this notion of real to sim, right? So robotics, again, is very, very fragmented in the sense that everybody has a very distinct use case. It's hard to kind of represent all of them at any given time out of the box, which means if people have the capability of, for example, taking a room like this and putting it in the sim, that means you are really training your robots in the scenario that you care about, in your kind of like the true value prop for what you're trying to do. And that's where a lot of these advances in generative AI are really playing a role. So this is actually a little snapshot of a drone in our AirGen sim actually living in a Gaussian splat world. So this is actually scanned from real data. This is all being simulated as particles using Niagara. So there is a certain limitation on how many particles we can have. But overall, the possibility is indeed there, right? So again, this is a very active area of research, both for us as well as outside. But the fact is, now you can go probably scan your lab, your workspace, or your abandoned mineshaft, I guess, if that's what you care about. But whatever it is, the fact that you can pull it into sim with maybe minimal effort, and now your robots can do 10,000 things in there, whereas you couldn't have done all of that in real life, it's huge. And obviously, this is also being supported through other technologies, like, for example, reality capture or general like photogrammetry tools. So again, there is a lot of potential in bringing real to sim and having your robots experience so many different kind of like branching kind of experiences in those worlds, and that's, I think, very, very powerful to build robots that scale into real world. And that's actually a huge thing in sim to real in general. It's almost like real to sim for sim to real. So it's a couple of hoops. Sorry, I think okay. And then there are some interesting things in the environments too that you want to simulate. It kind of goes back to environmental effects that I was talking about earlier. So these are some experiments that we've been doing with plugins and kind of like core Unreal technology on how do you make your skies and weather a little bit more dynamic? How do you give that level of control to the user? And obviously, if you're setting like weather conditions, for instance, and you're in this particular world where there's basically like a lot of water and kind of like an island, you would obviously want that to affect a ton of things in the scene. So the water has to be affected, and the objects that are in the water, like boats or something, they have to be affected. And all of this is really, again, the core thesis is that we don't want to do any of these things on like a per environment or a per scenario basis. All of these have to be kind of core capabilities that any environment can leverage. So again, this is a sample of how you would kind of tweak some sliders in the sim to affect the wind and affect the what is it, like dust and fog and snow and rain and so on and so forth. So having access to these and kind of leveraging particle effects for a lot of this actually takes us a long way in at least letting these robots experience not so perfect kind of worlds. And then the fact that you can also affect the camera imagery when you do this kind of stuff it's super critical. And the physics too. So there is the visuals, there is the physics, and then there is this spectrum of variations across that we've been enabling that really helps with some of these challenging scenarios. I think overall, the takeaway for us here was that, there is it's essentially, I'm trying to kind of articulate this the right way, which is there are so many things that matter when you are solving hard problems. If you are thinking about maybe like a surveillance drone or something on an island scene, you've got to get the water right, you've got to get the objects right, you've got the NPCs, maybe there are birds flying around, so you have to avoid those. So all of those things matter, and you really need, I think, again, a platform like, for example, Unreal Engine to kind of get all of those things in place and be able to target them, interact with them, vary them to some extent, and so on. Okay, so that's a little bit about the environments, right? So that's great. So those are all the sceneries and so on and so forth. But of course, then we come to this aspect of robots. So of course, the environments are nothing without the robots actually being able to operate in them. So what we do with AirGen is we have integrations with, for example, Chaos for all of the wheeled vehicle dynamics, and I'll talk about that in a little bit, and also just general physics in the scenes. But there are certain platforms like fixed wings, which Chaos it's not necessarily meant for that out of the box. So in Unreal's done a great job in actually kind of supporting JSP Sim, which is for those of you who might be aware, you know that it's a open source flight dynamics model, essentially, and it's supporting a flight simulator called Flight Gear, which is kind of popular out there as a free, easy to use kind of a flight sim there. So what I'm showing you in this video here is actually kind of a class of a drone that is using JSP Sim through the Unreal integration, flying over Google Maps being served through Cesium. So there's a lot of things coming together for a very interesting use case. And the good thing is through JSP Sim, because it's just like a generic flight dynamics model, you can actually go simulate any kind of a plane. I think you can go do Cessnas, you can do F-15s, you can do all different classes of like large and small kinds of planes. And that's one of those things, again, if you the right kind of implementation leads to scale, as opposed to maybe like hacking together one kind of a physics for one aircraft, which is what we've done in the past, sometimes. But obviously, scale is important, so you have to go back and kind of re-implement some of these things. But this is something that we're kind of like actively integrating as well, so that we can simulate different kinds of flight platforms and all the nitty-gritties that come with flying planes, which I'm not personally aware of. Nicola might have more to add there. But, so overall, that's something that we're working on right now. And apart from that, even when we talk about wheeled robots, I think wheel dynamics in general is easy enough to kind of put together. But there is also the notion of environmental physics, right? So you have to, like for example, in this video, we're looking at a forklift in a warehouse. It's easy enough to put a forklift in a warehouse, but it's not so trivial to have this forklift kind of go interact with objects and pick them up and put them in different places. So you have to think about the pallets and their like how do you set up their collision meshes and how do you make these forks, I guess, kind of like reach in and lift them in realistic ways and how do you simulate the weights and the physics and so on and so forth. So that's actually something we're actively kind of building out in scenes like this. So you have an example of a warehouse robot here. The intent is to build autonomous kind of forklifts, which a lot of people are interested in, right? But then you have to not only put the scenery in place and the robot in place, but you also have to get everything kind of worked out right with the physics and the failure possibilities and all of that kind of stuff. And to tie it all together, I mean, we have, again, different kinds of robots, leveraging chaos, leveraging JSP Sim, all of these different integrations, but also sensor models, like, you'd have to simulate different kinds of cameras, different LiDARs, and distortions, and noise parameters, and so on and so forth. So all of that is also very, very important to get kind of like true sim to real. And after we have the robots and the sensors and the scenes, I mean, you need this capability to really simulate, again, like I said, experiences, so simulate and generate data. So what we do for that is we leverage a lot of the, for example, Unreal navigation system for kind of like these ground truth nav meshes so that you know where your robots can go and they cannot go. And there are also means to kind of like do it in 2D as well as 3D. So we kind of rely on, for example, things like, I don't have that in this specific video here. This one's only showing a 2D navigation scenario. But kind of like these sparse voxel octrees that can build large 3D maps so your drones can fly in them, because otherwise it would be kind of limited to ground robots. But really, being able to have these ground truth kind of occupancy maps and the capability of planning paths from point A to point B, so that little red line is actually kind of like a ground truth plan that's being planned by the navigation system, although the forklift might not be following it very, very well. Everything needs a little tweaking to get right. This is actually great for you to simulate, OK, I need some behaviors of my forklift going from point to point, picking these boxes up and putting it somewhere else. And now if you do it at scale, you actually have a very useful data source, specifically in a warehouse with these forklifts, with their physics and so on. And maybe at some point in time, it's actually a warehouse that the user kind of scans. And it's actually their warehouse and in their setting and everything. So beyond that, the other interesting thing also is what people call domain randomization, right? So domain randomization is something that has a huge spectrum in itself. So in this little snippet here, I'm showing some capabilities from our sim, which are about how do you tweak the objects? Like, how do you place them in whatever places that you want? How do you multiply them? How do you increase scale and make them bigger and smaller? And you can change the texture and so on and so forth. And at the end of it, actually, you have a little snippet of a 3D octree, kind of an occupancy map that we built. But what domain randomization really gives you is the capability to really change the scene to your heart's content, right? So again, that's exactly what the promise of simulation is, so that you can go into these scenes and you can create all of these different variations of which your robots can get all of the different kinds of data that they want on even very unrealistic settings, or kind of like these long-tail scenarios or failure scenarios. And of course, I just wanted to spend a quick moment kind of talking about the integrations as well. So this is a little bit on the platform side of things, but we have some integrations on the AirGen simulator with things like these industry standard protocols for like hardware in the loop testing or software in the loop testing. And all of these kind of like tie in very nicely with the Unreal Engine layer, because if you can expose the right kind of like camera hooks or the hooks into the world for kind of variations or trajectories or data generation, it's very trivial to kind of go link them with any of these higher level tools that can do mission planning or operator training and stuff like that. And we've seen a lot of use for these sorts of integrations with the base sim, and there are kind of like things sitting on top that are speaking different kinds of interface languages, giving even somewhat like more non-technical people the capability to work with the sim and simulate different kinds of scenarios so that they can understand how a specific pipeline would work or a specific model would work, and so on. And over all of it, that is the infrastructural bit, because I made a point very early on that there is a kind of like a barrier to entry to robotics because it's perceived to be so hard. But this is actually where we found, for example, Unreal Pixel Streaming to be super, super useful, because now you can take something like that and abstract away all the complexity of accessing a sim. So you don't even need a GPU. Like, you can literally be sitting on a MacBook, and if you can stream a simulation from these remote sources, then pretty much anyone can access simulation. Anyone can and should be able to do all the things that I just talked about. Like, how do you vary robots? How do you vary trajectories? How do you generate data? Or at least just understand how a specific pipeline would work in your kind of like industry use case or something of that sort. So this is actually something that we do as a very core thing in our platform. So this is actually a video of Unreal Engine running like a drone simulation this is a synthetic forest fire detection scenario. So there is a world in Unreal that uses Niagara to kind of simulate, you'll see that shortly, synthetic forest fire. And this is actually a very interesting problem in industry right now. Like, how do you leverage drones to kind of detect and inspect fires? And what this is doing is there is a containerized kind of like an Unreal sim in the background on some cloud VMs. This is the front end that the user will see, which is all very kind of high level and easy to grok. So the streaming is happening in real time using pixel streaming, and the users can do like a collab sort of a thing. This is basically our platform. So you can go write Python code, and you can interact with the drone. As you can see, there is a little fire over there, and then you're using AI models in this demo video to kind of detect the fire, or get some segmentation data or something like that. And really, the intent here was like, how do you make all of this kind of stuff so super, super accessible? And being able to stream, being able to containerize, being able to put everything on the cloud, and it's a huge step in that direction. So, and the good thing about stuff like containerization and putting things on the cloud is that you can now also parallelize these things. So this is one way of using the platform, which is somebody just kind of goes and writes some basic code, and they're able to, for example, what's happening in the video right now is the weather is being tweaked. So you're now simulating a more complex scenario of this forest fire detection thing. But you could also run maybe 100, 200 instances very similar to this, so that you are generating 100x the amount of data, or 100x the amount of kind of like test results for your pipeline. So maybe if you're building a model, you would wish to test that in these varying kind of like scenarios and so on. And if you're interested, you can check out our platform at this URL over here. OK, so basically, those are some of the ways that we've been leveraging Unreal technology in creating high-fidelity worlds, creating high-fidelity robot dynamics. And really, what do you do with that? Like, how do you generate the data? How do you serve it? How do you access it? And so on. So this leads to a lot of, obviously, interesting use cases where we found the value of all of these things coming together, really helping close the sim-to-real gap, really helping folks, for example, plan out their missions and their pipelines and workflows in the sim and move it on to real. So this is actually the project that I was alluding to earlier with Raptor Maps, who are doing a very interesting kind of like cross-form factor collaboration for solar panel inspection. And as part of that, what we did was we reproduced a portion of basically a geo-referenced real-world solar farm. But the actual solar panels, which you kind of see over here, they're all kind of synthetic assets, right? So this is a scene that Raptor Maps had built in Unreal Engine. And then we were bringing in kind of like the drone dynamics and the sensors and so on and so forth. So there's a lot happening in this view here. But the main things are there is the Unreal simulation from AirGen kind of running over here. There is actually, some of you might know, this tool called Ground Control, which is basically like a mission planning tool for drones. So operators can go over there, kind of set up certain missions, and they're also able to, just similar to what we did before, they're leveraging something like Niagara to kind of simulate damage or fires and stuff like that. So again, a lot of pieces are coming together in a scenario like this. There is the drone physics, there is the environment, there is the sensors, and the higher level kind of mission planning tools. And it helps you kind of develop kind of like AI faster. Like, you could go develop inspection procedures, or you could go develop damage detection. You could go maybe even put in, like, for example, a large language model or something that's looking, or a VLM or something that's looking at all these images, giving you some insights into what's happening in your solar farm and stuff like that. And of course, the fact that there are two kinds of robots here means it opens up a lot of heterogeneous kind of robotics, interesting use cases there. And there is also this notion of a combination of like geospatial and synthetic, especially I talked about ground detail, right? So there is a problem with ground detail when it comes to Google Maps and stuff like that. But let's say, what if somebody wanted to do a drone that would go inspect cell towers? The asset for the cell tower would not look as great as you would want it, but that means you could still leverage something like cesium. This is exactly what we're doing here. So cesium is bringing in Google Maps where our drones are kind of flying in Unreal, but the cell tower asset is a synthetic asset, right? So this little thing over there that was kind of like placed in georeference in a specific location, and you could obviously cache the tiles for the rest of the scene, and you got your nice looking asset out there. And oftentimes a lot of people might actually have these models, like CAD models or something that exist in their workflow, so they can very seamlessly kind of ingest them into the sim. Obviously, there are you can ingest like OBJs and GLTFs and maybe USDs and all of these kinds of things very, very quickly. So that lets you, again, custom scenery means you've got maybe like a base level scenery from Google, but then you have your assets kind of located at very specific locations, and then the same kind of stuff. You can still access all the robots, you can still access all the sensors, you can do mission planning, and then in this particular case, where there's actually hardware in the loop kind of happening there, so there is a real hardware kind of like tied to the sim, so the dynamics are being, at least the estimation of the dynamics are being kind of driven by the real hardware through the drone PX4 stack. For those of you who might be in the drone space, you'll know. But another example where there's like a hybrid of geospatial kind of base scenery with some custom assets. And lastly, there are some cases where you actually need a full custom scenery, because there are parts of the world, for example, where the Google Maps tiles just don't cut it. They're often very, very 2D. They don't have a lot of fidelity. And this particular scene was intended to be an island in South Asia. So this was geo-referenced to that location, but there is not much in Google Maps that you can really use. So the bare minimum terrain is present, but then all of this entire scene was kind of like built custom. So all the nice-looking lighting and the variations in the trees and the water and so on and so forth, with like this airport, like I think it's an air base kind of a thing, so runways and planes and so on. And then you can start tying in the things just like the way we talked about. So you have mission planning, and then you have your different objects of interest that you can place, these AI models you can tap into, and this was kind of like an end-to-end scenario that we did with our grid platform. And maybe I'll skip ahead a little bit for kind of like a more in-the-weeds view of grid, kind of like running some AI object detection here in this scenery. And yeah, I mean, simulating large-scale scenes very efficiently has been a huge kind of boost in the way we've been trying to do these outdoor robotics. Okay, so I also wanted to spend some time just to go through a few points that are kind of like top of mind for us when we are thinking about what are these challenges that we are facing still, and all of those are opportunities, right? So it is still non-trivial, for example, to do rich behavior from agents, right? So it's okay. I mean, you can definitely build a bunch of scenes and then have these robots operate in many different ways. But again, like I talked about, let's say you want to create like a social robotics kind of scenario, then you need a lot of NPCs. Maybe the robot's actually interacting with them. They're actually moving. They're probably, maybe somebody's like picking up a bottle and giving it to the robot, and the robot's taking it to someplace else. All of those things are, they still require, obviously, a lot of expertise and effort and so on. So I think there is definitely a lot of interesting opportunity as robotics kind of like grows and scales. Like, how do you make those very easy to invoke or create? And maybe I just talked about robots picking up bottles. Contact-rich robotics is a huge thing today. I mean, people are very interested in building humanoids and manipulator arms at scale, and that means you're now concerned about deformables and stresses and very fine-grained kind of like physics details. And an open question, of course, is like, how do you do that efficiently, right? So yeah, again, in the context of Unreal, in the context of AI, like what is the right way to think about high-fidelity physics with contact-rich kind of use cases? Going back to environments, I think we've made huge strides of progress over the last few years as a community, but I mean, things are popping up on the radar so quickly. There is like Gaussian splatting stuff, for example. There is a new paper every week, almost, with some slightly more efficient way of doing it, or a completely different approach that really kind of like improves upon the state of the art. But how do we get ahead of that game? How do we leverage Gaussian splatting and nerfs and so on more effectively is a great question to ask. And there's also a lot of work happening in the USD world, right? So with the hierarchical kind of representations and all the different kind of advantages that that brings. So how do we think about USD, for example, in the context of Unreal? How do we integrate scenes that are like large scale things that are built as USDs, for instance? And just going on, in the environment side of things, there are still optimizations potentially in photogrammetry to sim. There is, things like procedural generation. Like, what is the right way to do it? That's a question. And just kind of like in the same vein as the NERF and the Gaussian splatting stuff, there is a huge potential in using generative AI for creating assets. These models are so good from going from like text to image or image to 3D or even text to 3D. So a very native integration with models like that means you can set up scenes and set up objects, very, very quickly. You can iterate between so many different possibilities. And kind of lastly, it is still a challenge to do very complex sensors, like physics-based sensors such as LiDARs, which have reflections, and IR, which has very kind of like interesting spectrum-based behaviors on metals and different kinds of objects. So yeah, how do you pull all of those in? What is a scalable way to do that in sim? And how do you kind of emulate accurate noise and so on and so forth? So these are some of the questions. I'm sure there's a lot more that we can brainstorm about, but some of the questions that we are thinking about as we try to build out our simulation stack and target more interesting scenarios in robots. And I think these are some of the interesting questions for the community in general to kind of discuss and move forward. With that, that's basically the end of my presentation. I'm happy to take any questions, and thank you very much for giving me this opportunity to kind of talk about the state of sim to real today.